All right, in 4.4 part 2, we are going to take a look at solving logarithmic equations. To do most of these, we are going to be rewriting these as an exponential. Right? So let's start with the simple one. Okay, if I've got log base 4 of x equals 3, we've talked about rewriting a log as an exponential. We would say the base of the log becomes the base of the exponential, and it would be 4 to the third power equals x. So now we have x by itself. 4 to the third power is just 64. Okay, so that's how we're going to solve a problem whenever we have a log equal to a number. So in our next example, we have a couple of steps before we have the log by itself. So we need to get one log equal to one number in each of these situations. So I would just start by subtracting 4. So we'll have 3 times log base 2 of x equals -3. Then I've got this 3 out front. I can divide both sides by 3. I'll have log base 2 of x equals -1. And now that I have a log equal to a number, I can rewrite it as an exponential. This would be 2 to the negative first power equals x. And now 2 to the negative first would be 1 over 2 to the positive first, or just 1/2. Okay? In our next two examples, it is the same idea. We just are going to have to solve a quadratic equation now. Okay? Now, I actually already have a log equal to a number. So I can go ahead and say, well, 6 to the first power equals x squared minus x. Now to solve a quadratic, I just want to get everything on one side equal to 0, so I'll subtract the 6 over. Get 0 equals x squared minus x minus 6. And now we want to x factor. Right? Two numbers that multiply to -6 that add to -1. I think that'll be -3 and +2. So this would become x minus 3 times x plus 2. And we'll go ahead and solve. So setting this equal to 0, I would add the 3 over and get x equals +3. Here, setting this factor equal to 0, I would subtract the 2 over and get x equals -2. So we get two solutions here. Now, I should have done this on the previous two problems, but whenever we get solutions to a logarithmic equation, we need to check to see if we get any extraneous ones. It is actually fairly common that we would end up with extraneous solutions in a logarithmic equation because we cannot take the log of any negative values. Okay, we talked about the domain of a log before, and we said whatever's on the inside of a log has to be positive. So that's really what we're looking for once we get our answers. We want to plug them back into any log in the original problem and make sure that whatever's inside of that log is positive. Okay, so if I plug 3 in, that would be 3 squared, which would be 9, minus 3, well, that would be 6. So we're good there. 6 to the first power would equal 6. If I plug in -2, I'll have -2 squared, which would be +4, minus -2. So I would get +6. So both of these end up working. Okay, but it is important to check for extraneous solutions. So in our next example, pretty similar, we've got natural log of x squared minus 6x plus 9 equals 0. So I already have one log equal to a number. I can go ahead and rewrite this as an exponential. But what's the base? I don't see a base. Remember that the base of a natural log is e. So this would be the same thing as log base e of x squared minus 6x plus 9 equals 0. Now, if I say e to the 0 power equals x squared minus 6x plus 9, I can solve. Now, anything to the 0 power is just equal to 1, right? So e to the 0 is equal to 1. Subtract that 1 over to get everything on one side equal to 0, and we'll end up with this. And now we can x factor. So two numbers that multiply to positive 8 that add to negative 6, I think that'll be negative 4 and negative 2. So this will factor into x minus 4 and x minus 2. And setting each of those equal to 0, we should get x equals positive 4 and x equals positive 2. So again, we need to check those in our original problem. So plugging 4 in, we will get 16 minus 24 plus 9. So that ends up being positive 1. If I plug 2 in, 4 minus 12 plus 9 would also be positive 1. So both of these are correct answers. All right. In our next two examples, we are going to have to use our rules of logarithms. Okay? I have two logs on one side of the equation here. In order to use the process that we've been doing, we need our equation to be one log equal to a number. Whenever I'm adding two logs together, I can combine those into a single log by multiplying what's on the inside. So I can make this log base 3 of x times x minus 2 equals 1. I can go ahead and multiply that together then, and just make this log base 3 of x squared minus 2x equals 1. And now I can rewrite this as an exponential. I can say 3 to the first power equals x squared minus 2x. Subtract the 3 over, and we can x factor to solve. So two numbers that multiply to negative 3 that add to negative 2. Well, I think that'll be negative 3 and positive 1. So this will factor into x minus 3 times x plus 1. Solving each of those then, we would get x equals positive 3 and x equals negative 1. So now we need to plug each of those into my original problem. If I plug negative 1 in, I will have negative 1 here and negative 3 here inside of the log. We cannot have anything inside of the log end up being negative. That means negative 1 is an extraneous solution in this case. If I plug in 3, however, I will get a positive value inside of each log. So 3 is my only answer in this case. All right. In the next example, again, we have two logs on the left side of the equation here. I need to combine those into a single log. Whenever I am subtracting, we would divide what's on the inside, right? So I can turn this into log base 5 of 3x minus 1 divided by 2x plus 7. Now that I have this written as a single log equal to a number, I can rewrite this as an exponential. We can say 5 to the 0 power equals 3x minus 1 over 2x plus 7. Again, anything to the 0 power is 1. So 1 equals 3x minus 1 over 2x plus 7. And now, to solve, I want to get rid of the denominator. So to do that, I will multiply both sides by 2x plus 7. The reason we do that is these factors will cancel out, and we're just left with 2x plus 7 times 1 equals 3x minus 1. Subtract the 2x over, add the 1, and we'll get that x is equal to 8. Again, we would want to check that in the original problem to make sure that we don't get any negatives inside of any logs. So we'll have 24 minus 1 is 23, and then we'll have 16 plus 7 is 23. So it works. 8 is our solution here. In our final two examples on the front here, we have logs on both sides of the equation. The property that we're going to use here whenever we have logs on both sides, we want to get one log equal to one log. Once we do that, whatever's on the inside of the logs has to be equal, as long as the logs have the same base. So here they both have base 7. If I've got one log equal to one log, I just set whatever's on the inside equal. So here, just subtract the x over, add the 1, divide by 2, and we'll get x equals negative 1/2. So again, I need to plug that back into my original problem. So I'll have negative 1/2 here, so that would be negative, oh, I'm sorry, whoops, I messed that up, didn't I? If I subtract 1, this would be negative 3, there we go. So negative 3/2. So if I plug that back into my original problem, 3 times negative 3/2 would be negative 9/2, plus 1 would be negative 7/2. I can't have that. I can't have a negative value on the inside of any logs. As soon as I see it creates a negative value inside of any log, that is extraneous. So in this case, this problem has no solutions. Okay? But the idea, whenever we get one log equal to one log, we can set whatever's on the inside equal. So in this last example, the first thing that I want to do is combine these two logs on the left. Since I'm adding, I would multiply what's on the inside. So this will become log base 2 of, and I'll go ahead and multiply. So x times x is x squared. X times 1 would be x. So now I have one log equal to one log. I can take what's on the inside and set that equal. So I'll have x squared plus x equals x plus 4. Since this is a quadratic, I want to get everything on one side equal to 0, so I'll subtract the x over. And actually, we could do this two ways. I'll go ahead and bring everything over to one side though. So if I subtract the x, those will cancel. Subtract the 4 over. And now this is a difference of squares. I could factor this into x plus 2 and x minus 2. So we would end up with x equals negative 2 and x equals positive 2. But again, I need to plug those back into the original problem and make sure I don't get any negative values. Well, obviously here, if I plug negative 2 in, I'm going to get a negative value on the inside of this log and on the inside of this log. Negative 2 plus 1 would be negative 1. That means this cannot be an answer. If I plug 2 in, I'll have 2 and 3 and 6, so we would be good. The only answer then to this problem is x equals positive 2. On the back then, we've got a couple of real-world application type problems dealing with logistic growth. So I mentioned this idea of logistic growth in the last section when we had that population example. So this is probably one of my favorite application ideas in all of our studies, because this is super applicable to lots of things, right? The idea that we can look at here is population growth, but this would apply to anything from inventory to modeling. I mean, anything in the real world that is capped, right? So we're going to look at animal population. So they're not capable of exponential growth, unrestricted growth, because there's limited resources, limited habitat, limited food. So this is our basic logistic model, okay? So we're going to do two examples here. First, We're going to talk about a fish population where we're given each of these values. So in this case, we're going to say that this equation, if I'm plugging 1200 in for m over 1 plus, and I'm told a is 11, times e to the negative, and my k, which would be my rate, is 0.2, and then t is time. So in this case, we're saying that t is measured in years. It can be certainly based on the problem what t is measured in. It could be years, months, days, hours, minutes. In this case, it's measured in years. And we always say that we're interested in t equals 0 as our starting point. Now, how many fish were originally put in the pond? Well, that's going to correspond to when t equals 0. So what I want to do is take this equation and evaluate it for 0. So I'm going to say 1200 over 1 plus 11 e to the negative 0.2 times 0 power. So if I plug that all into the calculator, we're going to just get exactly 100. Now the reason for that is that this whole portion here would be e to the 0 power, and anything to the 0 power is 1. So this just becomes 1200 over 1 plus 11, or 1200 over 12, which would be 100. Now for these examples, I'm just going to have the calculator already queued up. If you have questions or want to see how you type that into the calculator, please ask. I'd be happy to show you. Okay, so in this case, our initial population of fish is 100. So we want to then evaluate population after 10, 20, and 30 years. So again, I'm just going to take my equation and plug 10, then 20, then 30 in for t. So if I plug 10 in, I'm going to get about 482. Now for a problem like this, it makes sense to round to the nearest whole number because we're not going to have 0.18 of fish. So for this case, we would just say, the population after 10 years is about 482 fish. If I plug in 20 for t, we get 998.77. And again, we can round to the nearest whole number, so we can say about 999 fish. And then finally, if I plug in 30, I'm going to get 1,168. And again, just round that to the nearest whole number since we're talking about fish. Right? So these would be our number of fish after 10, 20, and 30 years. So in the final part of this example, we want to evaluate for large values of t. Right? In theory, we're saying that this population can't grow unrestricted. We want to see what happens as time goes on. It's going to approach a certain value. It's not going to grow infinitely. So let's plug in like 50 years. What happens after 50 years? If I plug 50 in for t, we've got 1,199. Right? So let's go even bigger. Let's see what happens after 100 years. How many fish are in this pond? Well, if I plug in 100, we didn't really change much. We've got 1,199.9999. Okay, so it certainly appears as though we are approaching 1,200. So here is the graph of this function. Right? We start out at 100. It grows quickly at first, but then we kind of level off and we approach 1,200. All right. So let's see the information that we can get out of this. Okay. We can first say as t approaches infinity, right? As t, our time value, gets really large, p of t, which is my function, approaches 1,200. Okay. In our formula, okay, as long as our formula follows, let me go back a little bit, follows this, there we go, this model here, okay, as long as we have m over 1 plus a e to the negative kt power, that m value right there is called the carrying capacity. Okay, That is going to tell me the theoretical maximum number of things that can be supported. Okay, that is my carrying capacity. So in this case, the theoretical maximum number of fish in the pond is 1,200. So if we graph this problem, we're going to have an asymptote here at 1,200. Now, in reality, in the real world, right, we're not just going to never get to 1,200, right? In terms of this pond, there will probably be more than 1,200 at some point, but limited resources will cause some of those fish to die off, and we would probably go back and forth across that line. But for our mathematical equation, right, we're going to model it like this. So let's take a look then at a problem where we have to create this equation. Okay, now I set up an actual model here, right? So I actually researched this, and these are actual numbers for the world population. So this number, the carrying capacity of the human population on Earth, is definitely debated amongst lots of scientists, but usually they come up with somewhere between 8 and 12 billion. So I picked 11 billion to say that that's Earth's carrying capacity. And then these are actual values as well. In 2000, the world population was about 6.143 billion. And then in 2020, the world population was about 7.795 billion. So there are a few things that we have to do to set up this equation. First, we know that 11 is my m, right? This is my m value. So I'm going to go ahead and plug that in for m. Now, the other pieces of information that we're given here are basically 2 points on the graph. It says in 2000, the world population was 6.143 billion. So we're going to say that 2000 corresponds to t equals 0. So that means that the point 0, 6.143 is on the graph. Then my other point would correspond to this piece of data. Okay, so if 2000 is t equals 0, then 2020 would be t equals 20. So the point 27.795 is on my graph. Okay. The first thing I need to do is solve for a. To do that, I am going to use this first initial point. So if I plug this into my formula, I know that m is 11, so I'm going to say 11 over 1 plus a times e to the negative k times 0 power, right? Because we're saying that t is equal to 0. And then that population is going to be 6.143 billion. Okay. So now I want to solve this equation for a. I've got a couple other values in there, but the important thing to recognize here is this. This would be e to the 0 power, and anything to the 0 power is equal to 1. So this is just going to become 6.143 equals 11 over 1 plus a, right? Then I can multiply both sides by 1 plus a. Then I'll go ahead and divide both sides by 6.143. And then subtract the 1 over. And we'll get a equals 11 over 6.143 minus 1. Okay, and then let's plug that into the calculator. So if we plug that in, we'll get that a is equal to this 0.79065600313. Now, generally, we would round our answers to 3 decimal places, but we want to think about this as like an intermediate step. So we can either write down, this whole big value, or I think an easier thing to do is to store this in the calculator. So if you hit the STO button and then choose a letter, in this case, since we're solving for a in our equation, I saved it as a. Okay? So that 0.79 value, okay, is what our a value is. So we can write our equation now like this. Now I still don't know what k is. To find k, my second step is to plug in the other known point. So my other known point we already wrote down was the point 27.795. So I'm going to take this equation, okay, this 11 over 1 plus. Now, since I stored this value as a in the calculator, I stored it as capital A. I'm just going to write it as capital A as I'm writing this out. So to the negative k times 20 power, and that's going to equal the population of 7.795. So now I just want to take this and solve for k. Okay, because remember, a is just a value. It's this. Okay, I'm just not going to write out that huge decimal every time since we stored it as a. So let's start by multiplying both sides by this whole denominator. So we'll have 7.795 times 1 plus ae to the negative 20k power equals 11. I'll divide both sides by the 7.795. Then I can subtract that 1 over. So now my goal here is to get the exponential by itself, right? I'm ultimately trying to solve for k. So if I'm trying to get the exponential by itself, I would also need to divide by a here. So if I divide both sides by my a value, I'll end up with this. Okay? Now I'm going to go ahead and put this into the calculator. So if we do that, we get 0.5200251239. So again, this is an intermediate value. So I'm going to go ahead and store that. Okay, and I'm just going to store it as b. Since we already used a, I'm going to store that as b. So now in my equation, right, so I go back here, I'm saying that this whole thing, e to the negative 20k, was equal to 0.52 whatever, but we stored that as b. That's a numerical value here. So now I have my exponential by itself. I can rewrite this as a log. So I'm going to take the log base e, and the log base e is just natural log, right? So we're going to say natural log of b equals negative 20k. Finally, divide both sides by negative 20. And we can put natural log of b, of that 0.52 value over negative 20, into the calculator. And we'll get this for my k value, 0.03269399077. So again, this is an intermediate value. Let's store this. So since we solved for k in our equation, we called this k, I'm going to store it as k. Right? So now we have our full equation. Okay, this is my equation to model the human population on Earth. Right? It looks ugly, right? But just going through that process, step 1, use the initial value to solve for a. Step 2, use the other data point to solve for k. And now we can use our completed equation to answer the question. So it says, predict the world population in 2100. So since 2000 is t equals 0, 2100 would be t equals 100. So we're just going to say p of t equals 11 over 1 plus, now this value we stored as a, so we can go ahead and leave that as a, times e to the negative, and then this value we stored as k, so we can actually just type in k into the calculator, and then t is going to be 100. So if I type all of this into the calculator, that's going to give me the estimated world population in the year 2100. So if we do that, we end up getting 10.679 billion. Right? So in this case, we can round this. This is our final answer, right? We can round this to about 3 decimal places. So what was that, 10.679? Oops, if I could spell, that would help. Okay, and this is actually pretty close to what they estimate, to what a lot of experts estimate the world population will be, because we are already starting to see that taper off. We're no longer growing exponentially as a world population. Okay, so I know that this was kind of a complicated example where we used real world numbers. Okay, but the three-step process. Step one, use the initial value that corresponds to t equals 0 to solve for a. Step two, use another data point, okay, plugging in to solve for k. And then step three, use our completed equation to answer whatever question they are asking. All right, that is it for this video. The final question is going to pop up asking you what questions you have.